the topic or the scope I want to discuss is about X-ray absorption, right? With a more focus on the soft X-ray absorption. This, in fact, relates to some of the communications between us and the beamline scientists. For example, I forward you a long email from Adrian Hunt from iOS. So he actually gave a pretty long comment on some of their fluorescence yield measurement, right? So I don't know if you have had time to read it, and if you read it, you had enough time to digest it, because I still feel it takes some time to digest, but that's the process, and we are all trying to figure out what's going on, so we can be more and more clear about the X-ray absorption, especially the soft X-ray absorption. Hard X-rays are kind of a routine transmission, right? So something routine. So I'll start with some general questions, right? And this is something I feel we always need to get reminded when we are using certain techniques, right? We use techniques not just to publish paper. If we do need that, we need to make beautiful figures, right? We need to some nice pictures to put in their papers. But for scientists, for scientific research, we know what we really care is actually the information, right? So information is really what matters. And so for X-ray diffraction, we have discussed this a lot of times, right? For diffraction, we care about atomic position, and and for some of the battery materials, care about the occupancy and the site, microstructure, etc. So those are information where we care, and what kind of software we use, just the tools to get those kind of information, right? So we need to keep the goals in mind. For the PDF, it's about the atomic pairs, right? So and I think a very interesting recent work from Shah is identification of the indirect correlation in S-band in the polymeric sulfur, and we have discussed there sometimes about this, this kind of a trick using the indirect contact to analyze PDF data. It's not something routine or something that has been used by other people. We haven't found any, but I feel one advantage of using the indirect contact is it can better isolate some unique features from other structural features. There's less overlap, because if you look at the direct contacts or chemical bonds, there will be a lot of overlap, right? But if we think about the indirect contacts, actually they are more unique, and there will be less overlap, meaning that we have more confidence in identifying some of their atomic pairs and also some of their unique structures. For XAS, we are concerned about the electronic structure, right? So I have said this many times, and for bulk probably, two things matter: crystal structure, or the atomic structure, and the electronic structure. They both matter very much to battery materials, right? So to understand electronic structure, there are several ways, and XAS is just one tool of that. And we also need to be reminded it's mostly probing the unoccupied state. If we're talking about the molecular orbital picture, we're talking about the LUMO, the lowest unoccupied molecular orbital, or the conduction band, if we're talking about the solid state, right? We're talking about the solid state conduction band. And there also, it has capability to probe the local structure, benefiting from the EXAFS part of the XAS. I'll talk a little bit more about this in the second part. And also, I want to mention RIX. So Arthur has been doing some RIX studies, and we just got the data from Wanli. It looks like some very interesting result we can further discuss. And the RIX is now very commonly used for identifying the oxygen redox signature for the battery community, and is becoming more and more popularly accepted. So we have been working with Wendy in the past on several projects, including one on the lithium carboxide that we use the RIX to identify the oxygen redox in lithium carboxide. And the RIX is in fact a part of the fluorescence process, but the RIX has its own uniqueness. What we need to talk about the RIX in a serious way. But I want to point it out, we need to have some understanding of this, the meaning of this, the terminology. So R stands for resonant. So we can ask ourselves the question, why resonant needs to be mentioned here, right? So, so why resonant? What's so special about using resonant energy? Resonant means that the incoming energy is close to the edge. For example, if it's close to the K edge, right, there will create the K edge, the resonance. So that's the meaning of resonant. Meaning that it's the incident energy is close to some specific energy that would excite the transition. So that's the meaning of resonant. And I stands for inelastic. So meaning that there's energy transfer incurred during the process, right? So some energy is lost. So the energy is no longer conserved and the momentum is no longer conserved. So that's why it's called inelastic. And we also need to think about why, the inelastic is mentioned here. So keep those things in mind. RIX is not topic for today, but it definitely is for the topic for our future lectures. We'll go to RIX, right? And the X stands for X-ray, and the spectroscopy. There's nothing special about those two letters, but we need to be reminded this RIX is a resonant inelastic process, and it's very unique. Actually, it's because it involves two processes that has some very unique features from either the absorption event or the fluorescence or the object decay that were mentioned today. So RIX has a lot of uniqueness. And let's go to the topic we talked about today, which is XAS, X-ray absorption spectroscopy. So I think this picture probably, is nothing new. You probably have already been very familiar with this. I just want to go through it again, and I want to propose a question at the end of this picture. And I believe thinking about this question may give you some idea why I want to talk about the following materials. So XAS is basically probing the unoccupied states. I would encourage you to think about states more, than just think about the bands of the orbitals, right? Because in the lectures on many electron systems, we know what really matters is the states, and states can be complicated. Right? So it's a complicated wave function that is unlikely to have an analytic solution. So there are ways to approximate the states, right? So we talked about term symbols, which have some unique energy levels, but just want to have some comfortable feeling toward the world state, other than just the orbital. The orbital is more has more narrow scope. State actually is more broad and it's more general. XCS can be measured in very direct way, which is through transmission mode, and everybody likes transmission mode, right? It's easy to operate. We just put sample there and the X-ray goes through. We measure the absorption coefficient, then we get the nice, beautiful looking spectrum, and we can do a lot of analysis on them. So everybody likes transmission, and most likely transmission can only be done at the hard X-ray beam lines, because we need sufficient energy to transmit through the samples, right? So once it transmits through, then we can measure the transmission. But even though this is very routine, we also need to be careful about sample preparation. So we need to be aware how to calculate the sample thickness. If we know certain formula, how to calculate appropriate sample thickness for transmission mode, right? So even though the experimental setup is easy, routine, but still we need to know, how to optimize the thickness for appropriate transmission measurement. So I don't know if I have covered this in one of the lectures, but if not, we can also talk about this more. But I'm confident Momin and Shar and probably also other people are also be aware about how to do the thickness calculation. In the transmission mode, we have this kind of correlation, which is valid. So we measure the absorption coefficient. So this is what we measure, right? We measure, to be more specific, we measure the current in ion chamber after the transmission and before the transmission, right? And we get the absorption coefficient. And this is basically extracted from the Beer-Lambert law. Beer-Lambert law describes how the X-ray flux decays when it goes through the matter, right? So actually, this absorption coefficient is something extracted from the Beer-Lambert law, but this is pretty straightforward measurement. And this absorption coefficient correlates with absorption event, meaning that if you have a high absorption coefficient, then that is saying you have a lot of absorption event going on in the sample, right? So you have a high absorption coefficient, and that happens at the sample for example, if we're talking about transdimensional KH, that happens at the edge energies. So if it is this is nickel oxide, and if the energy hits the edge energy, then we have a lot of absorption. The cross section increases a lot, and then we have a lot of absorption event going on. So the mu becomes very large at the absorption edge, right? But still, if the X-ray goes through the sample, we still have the Beer-Lambert law to follow. Just that in that equation, now this coefficient is pretty large, right? So we do have this kind of correlation, and the number of absorption events can be correlated to the LUMO or the conduction band information, right? Because if we have more all-occupied states, then we can have a more absorption event to happen. So that's basically a description of that. But I need to put a parenthesis here, because it should be the symmetry corrected conduction band, right? Because it is a dipole dominated process, and we need to follow the dipole selection rule, meaning that the orbital momentum needs to be changed by 1. So we need to have the symmetry corrected conduction band information. So for the dipole, it is either S2P or P2D, right? So that's something we need to keep in mind. We also have the quadrupole, but quadrupole is a minimal contribution compared in terms of magnitude. It is less than 1% of the dipole process. So dipole is a dominant process during the absorption, and the dipole selection role is a dominant symmetry selection role. But in general, we do have this kind of correlation that is valid at each step. So once we measure mu, which is absorption coefficient, we get some idea about their conduction band, right? Or the symmetry corrected conduction band. And this is the information we're looking for. And this is a very straightforward measurement, right? And if we look at a typical absorption spectrum, this is they're starting, and then we have the pre-edge, we have this kind of edge jump, then we have the oscillating part afterwards, right? And it's kind of fading away, small wriggles as we go to the high energy. Let's go to the question later. Let's look at the following diagram. So once we hit the absorption edge, then we'll knock out a core electron and promote the core electron to a normal, a lowest occupied molecular orbital, right? This is what happens during the pre-edge part. So we're promoting core electron to the normal. And as we increase the incident energy, so now we have more energy. So we can imagine like the pump, the electron pump is more powerful. It can promote electron to a higher level. But still, we can promote them to the conduction band, but still this electron is bound. It's still bound by the potential energy nearby. So this is a bound electron without any kinetic energy. It's still within the system. Just that electron have different states now. It's no longer core electron, but it's promoted to a conduction band, but still in the bound state. So this corresponds to something around here. For example, corresponds to the 4p state something, right? It's is in the conduction band, but still in bound state. And then it will increase the energy even further. Then we will reach the point where we promote the electron from core to the vacuum, where electron doesn't have any potential energy anymore. It is a free energy now. It is not bound by the whole system. At this level, the electron doesn't have a potential energy at all. So this is kind of a threshold. After that, it will keep increasing the incoming photons. This electron can gain energy, right? At this point, it is E0. After that, it will gain some kinetic energy. It will no longer have any potential energy. It has become a free electron, but it will gain kinetic energy. And as we gain the kinetic energy, and this electron is propagating out, and because it has the kinetics and is interacting with the neighboring atoms. So actually, because we know, now we need to think about the electron as waves, right? So this is the tricky part about thinking they're small particles. Sometimes it's easy to think about them as particles, right? We think of them as particles here, but now we need to think of them as about waves, because electrons are still waves. So now it's basically the wave propagating out, and it's scattered by the neighboring potentials exerted by the neighboring atoms. Then actually the waves will come back, interacting with outcoming the waves. So there will be waves oscillations around this absorbing atom, and giving rise to the oscillation of the absorption coefficient. So that's why instead of looking at a flat line, we do see oscillations here, right? But you see the oscillations are pretty small. So that's why people want to get their K cubic weighted examples, just want to emphasize the oscillation region. So we do have the oscillations coming from this kind of interaction, right? So this is the picture for the typical KH X-ray absorption spectrum that we analyze. And now we can come to this question. So we do have examples for the KH, right? So my question is, do we have examples for the LH? Maybe we can give 5 seconds to have a vote here. You can type your maybe answer in the chat. Okay, any clues? Maybe no. Sha said no. Okay, Arthur said no, and Dean said no. Mominar, what's your thought? Okay, everybody has the same answer, right? Okay, looks like we have a vote. Everybody agrees, but Shar, I thought you would actually give the yes answer, because I can understand everybody else may say no, but you just measured the LH of the iodine. Did you see examples?
Oh, all right. I'm sorry about that, because
Right.
I think theoretically it should have examples, because it always has a free electrons and it will interact with the neighboring atom. But when I think about my previous measurements, and I realized for those like transition metal LHs, I didn't see the examples, but I really forgot about the iodine.
Yeah, for iodine is because it's even at the average, it's very high energy, right? We still have about 5K. So it's still going through the sample.
Oh, okay, I see.
Well, to put it in perspective, this question is not easy, because I kind of devised this question, when I'm preparing this slide. So actually, I have some time to think about this. but you guys, I know you're kind of a corner, right? I give you about 5 to 10 seconds to think. So yeah, it's not fair to give a well thought answer, but I think this is maybe a good occasion that we can open this discussion about this. For the iodine LH, because we are using high energy at 5K, we're still going through the sample. In other words, we're still going through using the transmission mode, right? And once we use the transmission mode, and this kind of correlations they establish, and this kind of establishment is basically, I think at least it's the very important part, for you to have this kind of a picture, right? This picture is typically only valid if we have this kind of correlation. So for the iodine LH, we're still going through something like that, right? We just have a different cohort level. But you guys are actually, I would say 90% correct, because for most of the LH that we measure, mostly transition metal LH, we do not have EXAFS. One thing is we cannot go through the sample typically, because we're using an energy range around, the hundreds of EV. Like, for example, for nickel, it's about 800 EV something. It's not high enough to go through the sample. And also, we are not making direct measurement. In those cases, we're not measuring transmission, absorption coefficient. We're measuring different things, right? So for soft X-ray, if we limit our scope to transition metal LH, okay, let's forget about the iodine. Let's move back to transition metal LH. We have a limited energy range, and typically we do not measure transmission. We measure fluorescence or electron yield, right? So that's what I want to discuss. Okay. For the soft X-ray SoftXAS, we're approaching, we're using an indirect measurement. So this is a place that I'm trying to make a big deal of the soft X-ray, right? Even though we have done experiment ourselves, and there appears, also a lot in the literature, but since I'm trying to make a big deal of it, because I hope everybody understands that, what we do when we make the soft X-ray measurement. So we measure decay products. By doing that, we are kind of implying this kind of correlation, which may not establish every time. So we're kind of implying, okay, I'm measuring the number of decay products, right? Either the photons of the electrons, and I'm suggesting the number of decay products, they correlate to the absorption coefficient. They have some proportion correlation. And this absorption coefficient correlates to the conduction band information. Because, in the end, we're still talking about the conduction band, right? In the paper, when we talk about the information, we try to, extract something from here, but our measurement is something here. And this part is valid, right? Because the absorption coefficient roughly relates to the number of absorption events that roughly relates to the conduction band information with a symmetry correction, by the way. But this part is not always valid. Sometimes it's valid, and I think we are kind of fortunate if it is valid. But when it's no longer valid, what we see is the spectrum will be distorted. It's not something, something looks so strange, and there's something that we cannot use for data analysis, especially if we want to extract the conduction band information. So we talk about why sometimes it's not valid. But before that, we need to talk about decay, right? And we need to talk about why the decay process happens, and how that relates to what we measure. This decay process happening because during the absorption event, we generate a core hole, right? So in the previous picture, we see that this is the first order event. We have this kind of absorption, and the initial state is we have a field core electrons. After the absorption, we have a core hole here. The electron is promoted. So a core hole is left behind. And this is the final state for the absorption event, right? Initial state is the field core electrons, and the after absorption event, there's a hole. So this is the final state. But this is the final state for absorption event. It's not the final state for the whole sample, for the whole system. The system doesn't stop here. The system goes on because the system now realizes itself is in a very unstable state. There's a core hole. The presence of core hole increases the energy a lot. So that's the core hole instability. So the system doesn't stop at the absorption event. It goes further to the decay process. Because we have such an origin of instability, then the system decays to lowers the energy of whole system so it can be stabilized, right? So we will appreciate that, the lower the energy, the more stable the system is. And it is also true here. And it has the two decay processes. But before we go to the detail of the decay process, I also want to mention a little bit more about the core hole instability, because the core hole instability relies to the energy resolution we get in the spectrum. For example, if this is a 1s core hole, and 1s core hole is extremely unstable, which means its lifetime is extremely short. And in the physics picture, an extremely short lifetime means that the energy resolution, we get all the energy uncertainty is very large. It's a similar uncertainty principle following the Heisenberg uncertainty principle describing the position and the momentum, right? We know that in the quantum mechanics, there's a uncertainty describing position and momentum. We cannot describe them simultaneously accurately, right? And that similar role applies to the core hole lifetime and the energy uncertainty. If we have a very short core hole lifetime, then we have a large energy uncertainty, meaning that if this is a 1s core hole, then we have a very large energy resolution. The energy resolution is poor. It's typically around 1 eV something, and sometimes can be even larger depending on your instrument, right? Because the instrument can contribute to additional broadening. But if this is a transition metal LH, it is a 2p hole, because we're talking about the 2p electron excitation. Then 2p hole lifetime is much longer than the KH core hole. So the energy resolution for the LH spectrum is lower. And if we have a very nice instrument, for example, at AIS, then we can go to about 0.1 eV energy resolution, meaning that we have some very, very well resolved peaks in the LH spectrum. But if we do the RIGS, then can be even further improved. If you look at the picture for RIGS, you'll see that, in fact, the core hole is in the 3D orbital. The core hole is not in the 1s or the 2p. The core, we cannot call it a core if it's 3D, but you get the idea. The hole is in the 3D, and 3D hole is much more stable than 2p and 1s. So the RIGS has a very extremely high energy resolution. With very well a nice instrument, we can push down to something like 0.01 eV energy resolution. So that gives the very well resolved peak features, spectrum features of our RIGS. And that's one of the reasons that people want to pursue RIGS, because it gives extremely high energy resolution that provides possibility of deciphering what's going on in the system, right? We want more peaks. This is a general a trend, right? For XRD, we like more peaks because more peaks give you more information. You have more confidence in solving the structure, right? And this is generally true also for the spectrum. Okay, so much about the core hole instability. We said that the core hole is unstable and it will decay, and it will decay through two channels. One is through the fluorescence decay, right? So what happens here is now we have a core hole here, and the core hole is promoted to the conduction band. So we have the promoted electron here. Now the system needs to do something to bring down the energy. What it does is actually it brings down the electron in the valence orbital. So we have the originally electron in the valence orbital. Now this electron goes down to fill up this core hole. So there's no longer a hole here, but we know there's a core hole left behind in this valence electron, right? And you probably can already have additional thoughts that this would not be the end either, right? Because now we have the hole here, then we initiate some other decay process, and you're right. So this is not the end of the whole system. Now we have the hole here. There will be further events going on, but this, this is complicated of discussion. We'll just talk about this, the second order fluorescence decay here. And once this electron is brought down, and there's energy difference between these two energy levels, and the energy difference is emitted in the form of a photon. So that is the fluorescence decay. And we need to be clear about one thing. That's what mentioned in Adrian's previous email. I think that's a good point. This is decoupled process, meaning that this is independent from this previous absorption event, right? In the slide 1, we talked about absorption event, the creation of the core hole. That's the first process. This process independent from that. It's decoupled, meaning that what's the meaning of this? This means that no matter what kind of energy we use for the incident energy, right? Once we create the holes, we'll initiate this kind of fluorescence decay. And then let me be more specific by what I mean. So what this means is, for example, if we use a very high energy, let's say 5 keV photon to excite the sulfur sample. Let's look at sulfur. We may think that, oh, 5 keV is far from the edge absorption of sulfur, right? Then we should not get any absorption spectrum, which is correct. Yeah, we do not have the absorption SoftXAS spectrum as we see previously. But if we think more, we realize that 5 keV is enough, to excite the core electron to a free electron with kinetic energy, right? So it doesn't promote itself to the conduction band, it promotes to the kinetic energy region, that we can promote the core electron to an electron that has kinetic energy. What this means is it has the capability of creating core holes, right? 5 keV doesn't give us capability to do XAS, especially the Zinc part, but it has the capability to knock out the core electrons, creating core holes. What that means, whenever we have core holes, we have the core hole instability. Then we have the decay channel, and we have the fluorescence decay. So we'll still have been having fluorescence from the sulfur sample, right? So we can do fluorescence at 5 keV for sulfur, even though the absorption energy is not correct. But we do have outcoming photons. And because we can calculate the energy of the outcoming photons, it's basically the energy difference between these two, right? Because all the energy has been transferred to this photon, and we can calculate what's the energy difference between these two. And in the case of sulfur, we can tabulate all the possible energies. And using a detector then can differentiate the outcoming photon energy, we know its origin. We know whether that photon is coming from fluorescence of sulfur, right? I hope we are on the same page on understanding this, because this can be important. This relates to our understanding of the LISOS2 beamline capabilities. So this fluorescence process is independent of absorption event. Whenever we have the core hole formed, we have this absorption. We have this fluorescence emission. And because we can calculate the outcoming photon energy, then with our energy discriminating detector, we know where this photon, which decay channel gives rise to this photon. So that's the the practical parts of our understanding this fluorescence decay. Okay, in addition to fluorescence decay, we also have the Auger decay. So fluorescence decay is giving us the photons, and Auger decay is giving us electrons. But it's not that straightforward. It's not, it's not directly giving us the Auger electrons that entering the detector. I'll explain what I mean by this in the next slide. But at least we know in the sample, it gives rise to the Auger electrons. And what happens is this, we still have the core hole formation. It's unstable. We need something to fill up this hole, and it's coming from a valence orbital. Everything is the same from here, right? But what happens next is, instead of emitting a photon that takes up all the energy difference, actually it gives all this energy difference to another valence electron. They may not be in the same orbital, by the way. But this system gives this energy difference to this electron that is originally already there in the valence orbital. And this electron, after absorbing this energy, goes out, and as a free electron with kinetic energy. And this is the Auger electron. This electron comes from original system. So, okay, so we see the core hole again, then it's not hard to imagine that this is not N either, right? Indeed, this is not N, and the Auger decay will be followed by other decay process, which is more complicated. But yeah, let's just limit to Auger decay discussion here. So it gives off an Auger electron, and the energy of this Auger electron can be roughly calculated, by estimating of the energy level of each electron involved, right? We have the core electron valence 1, valence electron 1, valence electron 2. Then actually the energy difference is what is gained by this Auger electron. Another information I want to mention is, this is something I mentioned previously in the lecture. I want to mention again because I feel this is important. We need to have some idea about the percentage of fluorescence decay and the Auger electron decay. If we look at so this is some very rough scribbling, but hopefully you can understand what I mean. So the y-axis is actually the percentage. So 1.0 means the full 100%, right? So that's the full yield. The a-axis, I didn't draw it, but a-axis is actually atomic number. So the x-axis is the atomic number. So if we look at the solid line, this is the Auger electron decay yield, or the percentage. We see that for those element, it's dominant. It's almost to 1, right? It's contributing more than 99% of the decay process for the low-Z element. So for the low-Z element, it's dominated by Auger electron. So this is something I hope that we can all keep in mind. As we go further down the periodic table, we increase the atomic number. Actually, the Auger electron decay percentage is decreasing. And at the same time, the fluorescence decay is increasing. At some point, actually, they have their equal share. And the later, for the high Z element, actually, the fluorescence decay is the dominant process. So this is a picture I hope that we have in mind. And what this means for our experiment is, so for low-Z element, for example, carbon, oxygen, fluorine, etc., we typically get a very nice, beautiful looking TEY spectrum, right? No matter whether it's TEY or the PEY, partial electron yield or total electron yield, you will see that the data looks very beautiful. But we do get nasty data for some, fluorescence, either TFY or PFY for the low-Z element. That's typical. That's not because we did the experiment poorly or we prepared the sample poorly. and not the beamline scientists not helping us, but this is an intrinsic process because we have a dominant signal from the Auger electron decay process is dominant for the low Z element. So that's something we can keep in mind. And due to interest of time, I'll just discuss about the limit of the TEY of something that we need to be aware of for TEY. I will discuss the TFY, the fluorescent decay, for the next lecture. So for the next lecture, we'll discuss the limitation of fluorescence yield. What could be limitation and how to address them. Okay, so for the TEY, I think the good news is, in general, TEY spectrum doesn't have a distortion problem, and in general faithfully follows the absorption coefficient. So meaning that the TEY can be used to, as some sort of analysis of the conduction band or the unoccupied state. But there's some details we need to be aware of this. So what happens here? The TEY, in fact, we are counting electrons, right? It's outcoming electrons. That's all the electrons entering the detector. But we need to know some details. So we have the incoming photon. So let's say the photon hits the sample here, and here we have the Auger electron decay. So the Auger electron is produced at this level. And this Auger electron, once it gains kinetic energy, it wants to escape the whole material, right? It wants to escape the whole solid, and try to find some possibility entering the detector, the electron detector here. But during this process, the Auger electron would actually have further interaction with the neighbors, with this whole system, with the solids, because the electron has a strong interaction instead of our photons, which actually has a small interaction with matter. Electron, they do have a strong interaction. The consequence of that is the Auger electron will produce a lot of secondary electrons during this process. So this Auger electron is consumed. It will produce a lot of secondary electrons. It's a cascade of electron production here. And in fact, what enters mostly in the detector are the secondary electrons. It's not the original Auger electron from the decay process of the sample. So we do see there's some detail, some process in this process. So that's why I'm saying we're kind of fortunate, right? Because we have the Auger decay and we have the secondary electron, but still we get this kind of a correlation that's still established. We can still rely on counting the outcoming electron and correlate with the absorption coefficient. So I would say this is some sort of a fortunate event that we can utilize TEY as analysis, right? So, okay, I think that's what I planned for today. And I planned for about a 40 to 50-minute lecture, and I hope that we can have some time for some discussion and the digestion of questions, right, that can provoke our thoughts on this process. And next time I will discuss their fluorescence decay process. Right, we'll discuss the PFY or the IPFY and the RIX. Yeah, and yeah. So let's discuss more if there's any comments or questions.
Thank you. I guess, yeah. If I may, yeah. Thank you for the nice presentation. Could you just re-go over how the 5 KE like in the, I guess, the iodine system or whatever would, how like the 5 KE would knock out the core holes? You said like basically something that can't hit the K edge, how that knocks out the core holes. Can you go over that process?
Yeah. I think we do need to spend more time on that because that is an important aspect, right? Some of the facts, some of the things going on at beamline At SIX, it's basically a hard X-ray beam line, but they are doing sulfur fluorescence mapping, and this is also true for ISS. ISS is also a hard X-ray beam line, right? It's neighboring the QAS, and I just learned that they're also trying to do the sulfur and even phosphorus fluorescence mapping. To me, some time ago, it's something that kind of surprised me. Yeah, that I wonder why they do not have appropriate energy range, but still they're doing this kind of mapping. But then the discussion with several beamline scientists and about the whole process, I think help us to understand why this is doable. A key information, a key understanding is that we need to understand this fluorescence decay is independent of absorption coefficient. Well, it's not fully independent. We can put it this way: fluorescence decay, in fact, matters most to the presence of core hole. Let's put it this way, right? Can we generate a core hole in your sample? If we can generate a core hole in your sample, then we do have the fluorescence decay process, and the outcoming fluorescence photon can be detected by the detector, and the detector can tell which decay channel it is associated with. If we know the decay channel, then we know which element we're dealing with, right? Because different elements have very unique decay channels because their electron levels are unique, and the energy transition between them, they are unique. So if we know the energy of this photon, we know where it is from which element, right? Okay, so if we accept this part, then we understand that the key point is the generation of core hole. Then the creation of core hole, in fact, cannot be only be realized by those resonant energy, those edge absorption. For example, if we're talking about sulfur, we're talking about the 2.4 keV, right? Those can definitely create a core hole. They can promote the core electron to the valence and to the conduction band, to the vacuum, even to gain the kinetic energy. That's we discussed in the transmission picture. But even for high energy, let's say we just use a 5 keV, they can still create a core hole, right? They can create a core hole, just that the energy is too high. So they cannot promote them to the conduction band, right? Because the energy is too high, we cannot promote them to conduction band. We have to push them further. So the limitation is, okay, we do not have any electron going to conduction band, so we do not get the Zing's part, right? We do not have the feature in the Zing's part. But we do have electrons knocked out of core hole and going into the vacuum and gain kinetic energy. That's something can be done by the higher energy, right? So once this kind of event happens, then we get what we need, the core hole. The core hole is there. The core hole is unstable. The core hole will incur the fluorescence decay. And because the fluorescence decay happens between specific channels, right? We can only, it can only happen from some, they're well-defined, the orbitals with well-defined energy. Then once we detect the kinetic energy of the photon, we know which decay channel is associated and which element it is from. And that's why people can use high energy to do their elemental mapping for some low energies. Hope I have, I tried my best to clarify the situation. I hope we're clear on this.
I actually have a follow-up question about that. Do you think this kind of mapping can only differentiate between the elements, or it can also like tell what is a chemical species? For example, this is like lithium sulfur, that is elemental sulfur, something like that.
Yeah, so we can still think about this absorption process, right? And as I mentioned, if we use a high energy, now we no longer can promote the core electron to a conduction band, right? We have to push them further. Then we are losing the Zing's part.
Mm-hmm.
If you want to identify the chemical oxidation state, typically you rely on the Zing's part. right? So you do the normalization, you want to analyze edge shift, those kind of things. You're kind of relying on the Zins part, which relies on promoting electron to the conduction band or to the LUMO part, right? That's something cannot be done by high energy, right? So high energy cannot give us a chemical mapping of the low energy element, but it can tell us whether they are there or not.
Okay. Yeah, thank you.
Yeah.
I have a question.
Yeah.
So I was just wondering, for the total electron yield mode, can the detector differentiate between auxiliary electron and the secondary electrons?
The detector, by differentiating, we're always talking about differential energy. That's something can be done, right? So in the case of the fluorescence decay, we have a so-called the vortex detector. It can tell us, how much kinetic energy this photon have. Then we correlate this kinetic energy with some specific decay channel. The same is here. It's also true for the detector. The detector can only differentiate the kinetic energy. It can tell, which electron has, what is a certain kind of a kinetic energy. But I doubt that can be directly related to their object decay process. It is possible because if we look at this Auger process, you see roughly speaking, the energy of the Auger electron is well defined, right? Because all these energy levels, they are well defined. So actually the difference among them is also defined, meaning that for certain element, we have a certain well-defined Auger electron kinetic energy. And if the detector can detect the electron with that kinetic energy, we can at least tell this, okay, this electron should be from that Auger decay process. But the problem is, during this escape process, it initiates, other electron decay process. So whether that, if say that is a certain Auger electron, whether that is from this part or from this part, that is something we cannot tell.
I see.
Right.
Okay, yeah, I was just wondering because for this secondary electrons to generate from the Auger electron through the when it in the TUI mode, I guess these secondary electrons would be very close to the conduction band, so that it gets knocked out easily, and also get some kinetic energy from the Auger electron.
Okay, so this is a universal curve I mentioned in previous lecture, right? This is important for understanding the electron, right? The probing depths, those things. If we are trying to correlate the kinetic energy with the probing depths, the problem is we need to know which side are we on, which side of the curve are we on, right? Yeah, this is probing depths, this kinetic energy. For example, if we have a very small kinetic energy, actually the probing depths can be pretty high. But if we're talking about it increased their kinetic energy, then it's actually decreasing the probing depths.
I see.
Right. Until we reach a certain threshold, then this is kind of a monotonic change, the monotonic correlation between the probing depths and the kinetic energy.
So until a certain threshold, the probing depth is inversely proportional to the energy.
Yes. So depending on which side are we talking about? Right.
I see.
Yeah.
So on the left side of that curve, so that would mean that the Auger electron would be more surface sensitive than the secondary electron, because the Auger electron would have more energy.
Very good. You're right.
I see. Okay.
And that is correct. And in fact, Auger electron, there's indeed a technique specifically collecting Auger electron decay, and that is extremely surface sensitive.
I see.
So you're right. Yeah.
I see.
And if we go further along this curve, and in fact, the right part is the hard XPS, because XPS is also basically electron, right? It's a photon electron. So that part is discussing this part. So in that case, because we can give a tremendous kinetic energy to the electron, so we can go to pretty high, pretty further in this curve, So we can gain some, thickness over even hundreds of nanometers.
Yeah. I had another question out of curiosity. I mean, it's a little bit random. So I was just wondering about this X-ray fluorescence imaging to kind of map the distribution of the elements. How is it different than, say, other elemental mapping like EDX that comes with the SEM? What kind of like a difference in terms of mechanism, if there is
At
any?
least the spatial resolution is different, right? SEM, I assume you gather maybe on the order of a micrometer, maybe hundreds of micrometer, something. I'm not sure. But with the focused beam, we can easily access something like 10 to 20 micrometer.
I see. It's basically the size. I'd say the size of the beam. Probably not.
For SEM, you're scaling, right? I assume it's actually relates to your probing technique size. But for example, as SoftXAS, if we use the focused beam, we can go down even down to actually, I think even micro sub micrometer, hundreds of nanometers. That's even possible. But depending on energy, because the beam size relates to the energy.
Okay.
Yeah, but it should be much more resolved than EDX, right? It also may relate to the detector. I don't know the sensitivity of EDX, but using fluorescence and with with a good detector, we can mapping something at a ppm level. I don't know if ppm is something accessible in EDX.
I see. I'm not sure either. So yeah, thank you. Thank you.
Yeah.
Well, actually, I have one question regarding object electron. So I know that for XPS measurement, we usually can detect object peak in the XPS spectrum, and one of the characteristic of an object peak is that it actually varies with the energy. So I'm just wondering, like, what's the difference between like the TEY-XAS measurement and XPS? If we want to get information from object electron, are there any advantage of like using XAS or XPS?
Okay, first we talk about the difference between XAS and XPS. So XPS is you're knocking it out and it becomes a photon electron, right?
Yes.
It's basically photon electron effect, right? But for the XAS, you first create an absorption event. And the decay process is something flowing that absorption event. Right?
Yeah, I know. Yeah, I know their mechanisms are different. I'm just talking about the object electron. Like, are there a spectroscopy or some techniques dedicated to detect the object electron? Well, that's my question.
I don't know. Yeah, that's my honest answer. But I sort of remember when I was doing PhD, I sort of remember I came across some papers and discussing using the ultra electron yield mode to detect the very surface. As I mentioned, when using the electron yield mode, we can also differentiate the kinetic energy of the electron. So that's why sometimes we do have the PEY, right? So PEY is kind of selecting the electron energy with a certain range. So that's why it's partial. But we can be more specific, and I don't see why we cannot do this, since we can establish correlation between the kinetic energy of electron and the object decay process, right? So we can basically tell which electrons should be from the object decay process. Then I think that should be doable. But yeah, I do not know much about this, and I guess the best answer is that you look into the literature.